our president and CEO, Terrence Mulligan, up here. But he is just a frog's leap away, accepting an award on behalf of the foundation from the Immigration Institute of the Bay Area for the immigration initiative we started nearly 14 years ago that has helped almost 3,000 local residents become U.S. citizens. So he's got a good excuse. A couple quick notes before we begin. Our friends at Napa Climate Now are here, and they are hosting a climate summit next Thursday, March 26th from 3 to 6 at Napa Valley College. They left some flyers up front, and there's some information, or will be, some information up here behind me on the screen. Also a reminder for those of you that attend this often, tonight is not a crisp 60-minute program, it's a 90-minute program because this is a topic that needs a little more time to do it justice. We will be allowing some time for Q&A, so you've got these index cards and pens, and our staff will come around and collect those from you as you think of questions and hand them in. So I want to start with a few words of gratitude. I want to thank the elected officials that are here with us tonight. I think we might have Liz Russell here, who is representing Senator Chris Cabaldon's office. Our board member, Pat Clary, is here, and she's the president of the Napa County Parks and Open Space District. We have retired Napa Superior Court Judge Steve Croyer. We have former American Canyon Mayor and founding Napa Valley Community Foundation board member, Leon Garcia. Sorry, I knocked a battery on the ground. And we have Napa City Council member, Chris DiNatale, no relation at all. So to our wonderful, wonderful board and committee members, current and past, could you please raise your hand? Just want to say thank you. My incredible colleagues who are here helping out tonight, please also raise your hands. And then most importantly, I just want to thank all of you. You are the folks that show up for this community time and again. And if we have any of the high school students here who are part of the Schools for Climate Action, thank you for your work. You are building a better future for all of us. So for those of you who might not be as familiar with Napa Valley Community Foundation, we work side by side with local donors and nonprofits to tackle the most important challenges our valley faces. Those issues are sometimes thorny, like climate change or wildfire, and we believe that a prosperous community rises from a strong foundation. Every day we gather generous hearts and bright minds to solve the problems that lie beneath the surface of this beautiful place we call home. Because when we harness the power of our collective generosity, we become a force for good, making life better for everyone in the valley. And I hope some of you who come to this have that just about memorized by now. But truly, without the support of those of you in the room and the hundreds of others of you locally here in the valley that support us, we would not be here. And I am really proud to say tonight that since inception in 1994, we have distributed almost $120 million in grants and scholarships. So lately, we've been really focused on, among other things, two really urgent and timely priorities: expanding legal services and education programs for immigrants in our community, and strengthening the safety net as public funding gets, shall we say, a little bit iffy. Another really important part of our mission is what we're doing tonight, building a stronger sense of community. And that's what this Common Ground series is about. We do it roughly quarterly, and it's about bringing local people together for thoughtful, nonpartisan, fact-based conversations about those issues and challenges that face our valley. So that brings us to tonight. As you well know, climate change is one of those issues that's often framed as political or controversial. As our speaker tonight will tell you, it isn't. It's just science. And here in Napa County, whether we know or understand all of that science yet, and we'll understand more soon, we are already feeling the effects in our water struggles, in today's unseasonably warm temperatures, and of course, in our ever-expanding fire seasons. In fact, of that $120 million that we've expended to date, more than 30 million of that has gone to fighting fires and other natural disasters. So as a community, we're pretty good at playing defense. It is time to start playing offense. And just like we did with our immigration initiative that we launched 14 years ago, we are starting with research, data, and community education. So it is my pleasure to introduce Professor Andrew Isaacs, or Drew to those of us here who consider him a really good pal. Drew is a geochemist by training, a former NASA scientist, and one of the country's leading climate educators. He has been teaching at UC Berkeley's Haas School of Business for nearly 3 decades, helping future leaders understand how climate science intersects with business and decision making. He has also advised more than 130 companies worldwide on this very thing, and they're just little companies like Google or Toyota or IBM. So we are proud to be partnering with Drew right now on our new climate education program. And the idea is to bring this kind of clear, science-based information to our community that will help all of us, whether you're a policymaker or a high school student, make informed decisions going forward. And if you don't already know, Drew isn't just a global expert, he's actually a Napa local, so we're really lucky to have him here in our backyard. One quick warning before I hand it over to Drew. He has a bit of a reputation for inspiring people immediately to reduce their fossil fuel consumption, and I can personally confirm that. So I would strongly encourage you not to ask my husband sitting over there what happened to our savings account after I saw Drew speak only one time, and suddenly we had all new solar panels, battery storage, and a shiny new electric vehicle. So please join me in welcoming Drew Isaacs.
So consider that a warning. You may wind up with an electric car, I think is what that means. Okay, I'm supposed to put this thing on, right? This is, apparently we're live streaming this, and that's what this second mic is for, so we should be good to go. And what else do we have here? Well, first of all, thank you for being here. Julia, thank you for the introduction. I'm used to speaking to students. It's what I've been doing for about 27 years at UC Berkeley, which is another way of saying I'm used to speaking to groups where I have no idea who's in the audience. This is different. This is like a very large Thanksgiving dinner because we kind of all, hi mom, hi sis. It's more that kind of setting. So it is a joy to be here with you this evening, and so many of you are friends and all of you are neighbors. And also I want to say thanks for coming out on an evening when you could be doing many other things, especially with the beautiful July weather that we're having. Now, as Julia said, this is a very important topic, so we're allotting 90 minutes to it. I'm used to allotting 15 weeks to the topic. That's how long a semester is. So I might just leave a few things out this evening. You'll be happy to know I'm leaving out all the homework assignments, case studies, problem sets, and a term paper, none of which you have to do as part of this evening. Now, in this hour and a half, roughly, we're going to cover a lot of material. It's mostly going to be science. Because that sort of does a level setting for us. All of you know something about climate change or you wouldn't be here. The idea is to bring us all up to a little bit more knowledge. For some of you, it'll be filling in blanks. For others, there may be some surprises, but that's what education is all about. Now, if you want to go beyond this 90-minute class, there's two ways you can do that straight away. One of them is we are kicking off a more or less monthly program at the Community Foundation down off Trancas, starting in about May, that's going to be focused just on climate. And we're going to explore a lot of different aspects, kind of a little bit more like a semester-long course crammed into, well, many meetings, probably monthly, probably starting in May, and so you'll get an announcement about that. We haven't fixed the schedule yet, but this is a fundamental issue to the well-being of the Napa community. If you're not into that sort of thing and are more of a book person, the best book that you could read for an introduction to modern climate change is a book called Introduction to Modern Climate Change. The author is Andrew Dessler, D-E-S-S-L-E-R. He is absolutely one of the top climate scientists in the world today. He's a professor at Texas A&M, and he teaches a course by the same name. And essentially, that's the textbook for his course. So if you would like a undergraduate level introduction to what climate change is, with the physics, chemistry, biology, earth science associated with it, that's my field, and the implications for it from a policy point of view, that's absolutely the way to go. It's 15 chapters long. Each of them is very brief because it's 15-week semester. So self-paced, whatever you would like. Introduction to Modern Climate Change is the book I wish I had written. It's outstanding. Both of those activities, either reading Dessler's book or joining the monthly seminars on climate that we plan to kick off in a month or so, either of those will make you into something of a dangerous person. In that, you're going to know more about climate change than almost any group of people that you walk into. It's not hard, it turns out. And you become something of a dangerous person. You get disinvited to Thanksgivings and stuff like that, because you want to. But you don't have to become obsessive about it. But it's something that it's just better to know what's going on with climate. Now, this talk, because it's on climate change, it has some unhappy stuff in it. In fact, it's mostly unhappy. The last portion of the talk is going to be some what I like to call green shoots that are starting to appear in the world of climate change, because there are some things that are finally happening that are worth pointing out, worth highlighting, that absolutely amount to climate action. It's things that communities and individuals and companies are doing, and countries are doing, that is really addressing the problem head on. It's very, very, very early days. It's not dawn. I don't know the right metaphor to use. It's not even first light. But there's green shoots that are emerging, and I want to share those towards the end of my talk. So let's go ahead and get started. I will make a comment that my students often ask in my lectures, when do we get to the happy part? And the happy part of any problem is when you do something about the problem. And so, again, doing something about climate change is actually not complicated, nor, in my view, does it involve politics kind of at all. In fact, it's become straightforward economics. So let's go ahead and get started. I need a different deck than the one that's queued up, I think. Uh-oh. There's our IT department. The one thing you needed to do today was change from your slide deck to mine. That's the one right there. Awesome. Yep. And you do have little 3x5 cards on your seat for questions and stuff as they come up. This is like church. You're passing with a basket, but just paper is okay. You don't have to put money in it. You take money too. So, anyways, here we go. Let's go ahead and get started. In all of my talks, especially on climate, I try to connect the topic to what's going on in the world today. Gosh. What's going on in the world today that's connected with climate change? You don't have to look very far. Let's start in the Middle East. This is from 11:48 this morning, March 19th. Global energy under threat. Iran hits Qatar's liquefied natural gas hub. and there's a map of where that is. I'm going to change over to use a pointer. So this is the South Pars natural gas field in the Persian Gulf. There's Iran, there's Qatar, there's the UAE, etc. This is the world's largest natural gas deposit. And it has been producing natural gas for about 30, 40 years. That's what it looks like when it's the refinery that processes the natural gas here in Qatar is on fire. That's this morning. Here's just a pump jack for scale. So it's awfully hard to miss that the world economy up through to the present day is closely associated with the production and consumption of fossil fuels. And fossil fuels, as we will see, are the burning of fossil fuels, as we will see, is the main driver, the main forcing factor of climate change. There are others, but about 2/3 of climate forcing is the result of burning coal, oil, and natural gas, the stuff that we call fossil fuels. So it's also leading to acts of what I would call curiosity or desperation. This is also from this morning's paper. It's a little hard to make sense of this image. I'll tell you what it is. That's a person for scale. And this is the foot of the Rhone Glacier in Switzerland that they've put white sheets over in hope of slowing down the melting of the glacier. This won't work, by the way. When I first thought of this, I thought it was like some kind of modern art or something, and but no, they're throwing bed sheets over the ice in hopes of preserving the glacier. Oh boy, howdy! We're in an amazing world in which there's a lot of anxiety about the climate, and actions like this that do nothing at all, absolutely nothing at all, about the mitigation of climate change or adaptation to climate change, which are the two ingredients to any kind of climate solution. I want to quote from that same author, Andrew Dessler, who wrote this a couple of weeks ago. It's time to move on. It's worth pausing to appreciate what fossil fuels made possible. Coal, oil, and natural gas powered our civilization for the last 200 years. I don't think that's an understatement. But the transition to renewable energy isn't a rejection of that legacy. It's the next chapter, and it's a better one. And I will add, it's cheaper too. When I started teaching courses on climate change at Berkeley, it's about 20 years ago, none of the solutions that exist today existed then. Now I'll say, 20 years on, the problem is much worse, and the solutions are much easier. 20 years ago, the problem was less worse, and the solutions didn't really exist. They do today, mainly in the form of renewable energy. So that's a quick intro. Part one. How do we know about the climate? Well, currently there's more than 21,000 weather stations in operation around the world. There's 80 here in the Bay Area, at airports and all over the place. There's one up in Angwin, there's one at the Napa airport, they're all over. They record on a continuous basis things like temperature, barometric pressure, humidity, all sorts of things, winds, and they report typically every hour or so by one or another means of telemetry. They're all over the world. We get about 200,000 monthly average temperature measurements just on the land surface of our planet. Earth is about 30% land, about 70% ocean. And we get about 14 million or so sea surface temperatures measured annually. So these are the numbers for 2025, 2026 will be similar. Each year, new weather stations are installed, old ones are taken out of service and so on. But we have an enormous amount of data about what's actually happening to our planet, in particular, the variable of temperature. So it allows us to understand what's happening. And I'm going to focus a lot today, not on projecting what the year 2100 is going to look like, or 2200, or somewhere out in the future. We're going to talk about what's happening now and the data that we have for it that is measurable today, and what we can measure from the climate record, which is really the geological record, okay? All of that data collection allows us to produce images that look something like this. Here's the Earth, the continents are outlined, and every place on Earth is color-coded according to this temperature scale here that you see at the bottom. And I'll explain what this means. For the year 2025, let's pick a spot, say London, England, right there. London would have recorded some hundreds of thousands of temperature measurements from their many weather stations. And data at the same locations were obtained continuously through most of the 20th century. So we could say, hey, in 2025, what was the average temperature for the whole year, night and day, January through December, in London, compared with a 30-year average in the mid-20th century, 1951 to 1980. And this is typical of how climate data is done. We'll ask the question, how is it now compared to a benchmark period of typically 10 to 30, sometimes 50 years? And that allows us to say, oh, London is warmer now. That is a shade of orange or so. So I would look here and say, okay, London's about 2 degrees Celsius warmer, meaning about 4 degrees Fahrenheit warmer, over the course of the year now than it was in the mid-20th century, okay? And so on for the whole planet. Now there's patterns here. At first it looks a little bit like, I don't know, modern art, but it's not. There's actual patterns here, and I'll point them out. Pattern number one is that the land is heating up faster than the oceans. It's not everywhere like that, and each year will be a little bit different, but if you look at coastal China, that's quite apparent. Or even if you look here in the Middle East, you can see that the Arabian Peninsula, which has the Persian Gulf on one side and the Red Sea on the other, is a little bit darker. Even though these are narrow bodies of water, the temperature difference is apparent. Europe is generally warmer than the adjacent part of the Atlantic. The western United States in particular is generally warmer than most of the oceans. And we've been predicting this for decades, and we're now just observing what we've been predicting. The oceans don't heat up as fast as the land because they're made of water. And water mixes in a way that rock does not. And so currents and wave action and other kinds of mixing phenomenon help the oceans to push heat downward. It's not that the oceans aren't heating up, they are. But the sea surface isn't heating up as fast as the land because the oceans have the ability to mix in a way that rock doesn't do that. The second difference is that water is more conductive of heat than is land, and therefore, again, heat is pushed downward through conduction, not convection, conduction, and as a result, the oceans aren't heating up as fast. That's bad. And the reason it's bad is because most life on Earth is on the land, not just human life, but any life on Earth. Most of it is on the land. And so the land is heating up faster than the oceans. You'll see data, I'll show you some, that takes a global average of temperature increases. It's a little bit distorted simply because most of the surface of our planet is water and therefore is not heating up as fast as the land. If you look just at the land, you'll see much faster rate of warming. Another pattern is that the higher latitudes, the farther north you go, is heating up faster. That too has been predicted for decades. We're now observing it on a continuous basis. Why the higher latitudes? Well, because they used to be covered with snow and ice. And that snow and ice is now melted away because of the fact that the planet has begun to warm. And so snow and ice, which is white, reflects sunlight back into space. With the snow and ice gone, the darker land and the darker Arctic Ocean below heats up faster, which makes it harder for snow and ice to form each winter. The name for that is called Arctic amplification, and we see it a little bit in the southern hemisphere, near the South Pole, especially the Antarctic Peninsula, but it's really clear that higher latitudes in the north are heating up much faster. A couple other patterns that are interesting. India is not heating up as much as the rest of Asia. Why? Well, India's got its own kind of weather system due to the Tibetan Plateau, the Himalaya Mountains, and so on. So it's kind of isolated. But the main reason is that India burns a lot of coal to make electricity. And coal doesn't burn very cleanly. It puts a lot of soot and ash into the air. And so India has this kind of umbrella of soot in the air that leads to problems, respiratory problems like asthma, emphysema, and the like, but also is shading the Indian subcontinent. Feeling better? If they stop burning coal, India will catch up to the rest of Asia. So that's why there's that anomalously cool area there. Another one is up here, the North Atlantic. There's actually some blue off of Greenland, and that's due to the fact that the sheet of ice on Greenland, which is about a mile thick pile of ice on Greenland, is melting very fast and is therefore dumping cold water into the North Atlantic, and so that strip of blue or white there is what's going on. There's another thing that's worth pointing out, and that is the whole planet is warmer. There's almost nowhere on Earth that's cooler than it was in the mid-century, or even the same, which would be white. All right, so the whole planet is various shades of yellow and orange and red, meaning the whole planet, to varying degrees, has heated up. Okay? So that's a good place to start. Now, here's another way of looking at it that's numerical. Maybe a little bit harder to see than the map, but it goes back farther in time. In fact, it goes all the way back to January of 1850. 1850 is about the time when we started to record modern temperature measurements. Thermometers have been around for hundreds of years, but people weren't writing down the temperature measurements that they were getting. The recording of weather data really started in around 1850 or so, mainly in cities like New York and London and Paris, but eventually worldwide. So the precision of data from that period isn't great, but the accuracy is perfectly fine. Their thermometers are no worse than the ones we use today. There were just fewer of them, and not a lot of people were writing down data. So this chart shows the temperature every single month since January of 1850, January through December, every single year, and it's color-coded in these shades of blue from 1850 up through about 1950. And so the temperatures on our planet would be, and this is relative to an annual average, pretty much wasn't changing until about 1950. Beginning in the 50s, we start to see temperature changes, and the colors give that away. So you can start to see these greens and yellows, and that's from the more recent years. And the past 3 years, 2024, 25, and the current year, 2026, are shown in bolder colors up on the top. Now, this is handy because it's, again, month by month, we can see actually we're consistently warmer month after month, year after year, at the present time than we were at any time in the past. Now, journalists will write headlines like, "This year was the hottest." It doesn't quite give you the message that you want to absorb about what that means. It's not, because it makes it sound like it was an anomaly. It was like an event. It got hot and then it'll get cold again. It's not getting cold again. It's staying hot. And the anomaly itself is running about 1.5 degrees Celsius right now. That's where these past 3 years have been. About 1.5 degrees Celsius warmer on average, the whole planet, including the oceans, which stuff heat downward and therefore stay a little cooler. So that shows up a little bit better here in this numerical chart than it did in that strobe picture of the Earth that we saw a minute ago. Okay. Now I'm going to use the term climate change a lot. Climate, you already know what that means. Climate is long-term weather. It's if you average long periods of time, a year or 10 years or longer, we call that the climate. So we would say, oh, Napa has a certain type of climate that's different from, say, Mendocino County, perhaps. So climate is long-term weather, but the term climate change is a bit of a catch-all because there's a lot of things that are happening as a result of the burning of fossil fuels that don't have anything to do with weather and are not good. For example, all of that combustion of fossil fuels that puts all that CO2, carbon dioxide, into the atmosphere is causing the oceans to acidify. Why? Well, because the oceans are not isolated from the atmosphere. The sea surface is where the oceans and the atmosphere touch each other. And so because there's wave action at the sea surface, a lot of atmosphere is entrained into the oceans. And that gas, CO2 and oxygen and other things, dissolve into the oceans. Well, when CO2 dissolves into water, it forms carbonic acid, like in this stuff, which is why a flat beverage doesn't taste very nice. It's lost its CO2, and with it, the carbonic acid that was in there. So climate change includes things like the changes we're making to the oceans, soils, species distribution. They all fall into this bucket of climate change that has really not much to do with the weather. For example, we've been living in Napa now for nearly 30 years. We have a water well that we monitor the level on about once a month or so, and we're seeing, even though the rate of pumping is constant, we're seeing steady decline in the water table that is likely the signature of the drying out of soils, meaning there's less infiltration of rainwater feeding the aquifer where we live. That's a 20-year-long longitudinal record of a single water well. But we see this elsewhere as well. So the fact that the aquifers, even for constant pumping, or even if you're not pumping the well at all, will slowly go down is due to the fact that the air is warmer at the surface and therefore there's more evaporative loss of soil moisture. So there's a lot of things that are related to climate change that go far beyond the weather. All right, I've hinted at the problem of carbon dioxide. And I'm not going to hint anymore, we're going to drive a bus right into this. So the atmospheric concentration of CO2 is the highest it's been in at least 2 million years, probably more like about 5 million years. CO2 is the main gas that we humans are adding to the atmosphere. It's accumulating in the atmosphere, and it's driving the warming that is the main motive force of climate change. Actors number 2 and 3 on the list are methane, CH4, nitrous oxide, N2O, and these are also gases that we are adding to the abundance of in the atmosphere, and they're the highest in at least 800,000 years, possibly longer. If you take the longer version of my class, we can go into why we know this stuff, but we'll make these slides available to you, and for your reading pleasure, I always include references. There's just a little pro tip if you're going to teach climate change, show where you got the data. So, and you can sometimes decode this as the Intergovernmental Panel on Climate Change, etc., but I just leave it in the link in the raw form so you can see where the data are coming from. Okay? So what's the result of these increased concentrations of greenhouse gases that trap heat in the atmosphere? Well, the last 10 years include all 10 of the warmest years ever recorded. There you have it. To me, that's what a journalist should write, not last year was warm, because it makes it sound like, well, the year after that, well, climate's always changing, goes up and down, and yeah, it does over millions of years. And the last 3 years are the 3 warmest years ever recorded. I'm going to show you plots of this so you'll see how this plays out. But you've already seen in that numerical, that color chart, that in fact the pattern's clear. The climate isn't what it was when you were born. Or as I tell my students, the climate isn't what it was when your grandparents were born. Try to make it relatable. In fact, the big accumulation of greenhouse gases, especially CO2, began at about 1950, and the earliest traces of warming also began at about 1950. So it's about 75 years or so of clear evidence. Part two. We're going to talk about greenhouse gases now because it's impossible to go forward on any discussion of climate change without doing that. So we're going to take a little journey. Fourier to Keeling to Vostok. Fourier was a person, Keeling was a person, Vostok is a place. Here we go. To understand what we're doing, you need to know a little bit about the Earth, which is the object. My undergraduates, I have to explain, that's the Earth, that's the moon. They're not actually this close. I did that so that they'd fit on the same slide. But they are shown in color, and they're shown to the same proper scale relative to each other. As moons go, Earth's moon is very big. Most moons are just a piece of rock. Earth's moon is huge. As planets go, Earth is pretty small. And so although there's a difference in, a ratio of radius of 6:1 or something like that, they're actually not that different in size. The moon is just a little bit too small to have an atmosphere. There just isn't enough mass to the moon, therefore there isn't enough gravity on the moon to hold light things like oxygen and nitrogen and other gases. It's just a little bit too small. Earth, somewhat bigger, is barely big enough to have an atmosphere. Earth's atmosphere is really thin. That's why when you look at it, you can see the continents. There they are. You're looking right through the atmosphere. You don't think about it, but it's like, yeah, you know what'll happen tonight? You can look up and see stars. Probably. So Earth's atmosphere is really thin. It's thin both in the sense that it's not very dense, and it's thin in the sense that it's not very tall. And you can see that if you look at edge on. For the moon, it's just the darkness of space right at the horizon. It's a sharp line. For the Earth, there's a blue band here. You can see the cloud tops and a blue band, a dark blue band. That's the entire atmosphere. There's not much of an atmosphere on our planet. That's the reason why climate change is a problem, because we add gases to our atmosphere in tonnages that are enough to modify the concentration of this atmosphere. If we lived on a planet with a thicker atmosphere, I would be out of a job. This wouldn't be an issue because it'd be so much harder to modify the makeup of our atmosphere. On Earth, it's real easy because we don't have much of an atmosphere. And so adding gases to it changes the physics of our atmosphere. Here's beautiful Lake Hennessy in Napa County. This is what the air in Napa County consists of. In fact, it's what the air anywhere on our planet consists of because the atmosphere mixes very, very rapidly, a time constant on the order of about 6 to 8 weeks. So you get very rapid mixing of the atmosphere on our planet. It's mostly nitrogen, that's what you're breathing, 21% oxygen or so, and about 1% argon. So that's what you're breathing in. The difference, the trace gases are trace gases. They're not very abundant, but they are very significant. So there's an important difference in how these gases behave and how these gases behave. These gases are transparent to your eye. They're also transparent in the infrared. Infrared means heat. So your eyes can't see infrared. You can feel it with your hand. You feel heat with your hand, but your eyes can't see it. So these gases are transparent in the visible range, meaning the colors of the rainbow that your eyes can see, and they're transparent in the infrared. These trace gases are also transparent to your eye, but not so transparent in the infrared. In other words, they block heat. They trap heat. And that's why we call them greenhouse gases, because they retain warmth. The metaphor that's always used, and it's a good one, is that greenhouse gases in the atmosphere act like a blanket. When you throw a blanket on your kid, the blanket doesn't warm up the kid. The blankets don't generate heat. The kid does, but the blanket traps the heat. Now, the physics of how a blanket works and how greenhouse gases, that's different physics, but the metaphor is apt. So greenhouse gases in the atmosphere act the same way a blanket does. They trap heat. They retain heat within the Earth. So what are these greenhouse gases? Well, you've already heard of three of them, very familiar: carbon dioxide, methane, nitrous oxide. And those are the three that matter the most. I'll say just a word about these others on our list. So CO2, carbon dioxide, mainly we are adding that to the atmosphere by burning coal, oil, and natural gas. That's about 2/3 of the whole climate story right there, the burning of fossil fuels. Fossil just means old, taking these hydrocarbons out of the ground, coal, oil, and natural gas that have been there for millions of years, setting fire to them, and putting the waste gases, CO2 mainly, into the air instead of putting it back in the ground. If we put the exhaust from burning coal, oil, and natural gas back into the ground, I would again be out of a job because we wouldn't be dealing at all with climate change. But we never have. We've always burned fuels. The tailpipe on your car goes into the atmosphere. The exhaust flue on a power plant, if it's burning coal or natural gas, into the atmosphere. The exhaust from a jet engine on an airplane, into the atmosphere. And so, tragedy of the commons, we're putting these waste gases into the atmosphere. And that's about 2/3 of the climate story is the burning of fossil fuels, releasing CO2 into the atmosphere. Methane and nitrous oxide together account for most of the other third of climate forcing. Methane is we're adding to the atmosphere mainly the result of the beef and dairy industry, cattle and other ruminants. There's other sources as well, but that's an important one. Nitrous oxide we're adding mainly through the overuse of nitrogen in fertilizer. And again, in a short class like this, we won't go into any more detail. There's a lot of other gases here that are greenhouse gases with complicated names. You don't need to memorize these. They all contain the element fluorine. You can see the element F in all of these formula. We sometimes call them the fluorinated gases. Those are all synthetic. None of them exist in nature. We use them as refrigerants and for industrial purposes. If you have an air conditioner or a freezer or a fridge, almost certainly you're using one of these. And when that freezer, fridge, or air conditioner breaks and you get a pinhole leak from the refrigeration loop, that gas goes out into the atmosphere and acts as a greenhouse gas. These numbers give you a sense of relative potency. Normalized to CO2, we assign a potency of 1, and all these other greenhouse gases are more potent than CO2. The good news is every single one of these greenhouse gases listed here, other than CO2, has a half-life. It breaks down in the atmosphere mainly due to ultraviolet light and other things. They break down naturally. The bad news is CO2 doesn't break down. It's a very stable gas, essentially has an infinite half-life. And so it just, by and large, essentially accumulates in the atmosphere, cycles in and out of plants, cycles in and out of the oceans, but it doesn't go away except in geologic time frames. It's very slow. Remember, I'm a geologist. If a geologist tells you something happens slowly, believe them. So CO2 doesn't just linger, it's essentially forever. It's our generation's greatest legacy. All right, so what does it look like? So global CO2 emissions from fossil fuel combustion from 1900 through to the present, there it is. The vertical axis is gigatons of CO2, that's just a unit of mass. Gigatons means billions of tons. And what you can see is, emissions of CO2 from burning fossil fuel didn't really start until maybe about 1950 or so. And it's been pretty steadily rising ever since. There's some zigs and zags. There's the pandemic. Remember that? Okay. A few years, 10 years from now, I'm sure if I'm still teaching, my students are going to go, what's that? That's the pandemic. Here's the global financial crisis. That was the previous time that the world ended. And each one of these major economic disruptions means there's less fossil fuel being used for a brief period, and then the economy rebounds. And that's what these little zigs are here. These downward zigs here are the oil shocks of the 1970s and early 80s. That down tick right there is the recession after World War II. So downturns in the economy are reflected in that we burn less fossil fuel. All right. But the big story here is that it wasn't until the post-war period, meaning about 1950 onward, that we really started to burn coal, oil, and natural gas. And what this is the rise of the middle class in this era here, where families would have an automobile, or maybe two, or these days 5 automobiles for a family of 3. Fly by air. You know, your great-grandparents, your grandparents, certainly mine, never traveled by air. Never. Now you don't really think much about it. So yeah, fly to Mexico for Easter for why not? And so this is the rise of the middle class in the US, Canada, Western Europe. And then this last leg up here from about 2000 onward, very steep, is the rise of the middle class in China. You need hundreds of millions of people driving cars, using electricity and air conditioners, flying by air, and all the other things that we do. It's not 1 or 2 people. And amazingly, even World War II, which was highly industrialized, it was nothing compared to the level of fossil fuel consumption today. Quite remarkable. And I want to point out one other thing here, and that is the growth has been roughly linear. I didn't attempt to draw a regression line or something through this, but it gives you a sense that, in fact, the burning of fossil fuels has been growing pretty steadily. Now, I'll mention now that one of the green shoots that's appearing is that it appears that we are slowing this down. Last year, this year, next year, somewhere right about now, we're probably at about peak combustion of fossil fuels. We'll come back in 5 years, we may have seen this roll over. Maybe not, but it's looking like it's slowing down. You can't really see that here because it's happening right now. But the main reason for this is China is hell-bent on not using fossil fuel for anything that it doesn't have to. Can you guess why China might want to get off of the fossil fuel habit? It's incredibly obvious now, given the wars in Europe and in the Middle East, that relying on foreign oil is not a great strategy for any part of the world. Domestic, that's another story. But so mainly this is rolling over, not so much due to changes in Europe or the US, but due to China reducing its dependency on burning fossil fuels, especially oil. Okay, I want to just take a minute about who figured out this connection between fossil fuel use and global warming or warming the atmosphere. And it started over 200 years ago. This guy, Joseph Fourier, French mathematician, was actually the first person to propose that the Earth is warmer than it should be because of something in our atmosphere, some gaseous species that must be retaining heat. The Earth is 93 million miles from the sun. It's pretty far away, and the sun's not that bright. So how come the Earth is pleasantly habitable? He was the first person to think about this and write about it. 3 years later, a French chemist actually developed the first mathematics around what we would come to call the greenhouse effect, speculated that water vapor and CO2 are what's trapping heat in the atmosphere. This is 200 years ago. Now, there it sat for 30 years until this person came along, Eunice Newton-Foote, an American chemist, did the first experiments to show that if CO2 in the atmosphere were higher, the planet would be warmer. Check out the year. That's 4 years before the American Civil War. This is a long time ago, right? These are also very simple experiments to do. You could do them at home. She did them at home. She did them in her kitchen in upstate New York. Published the results in a journal called Science. It's still around today. Would you be surprised to hear that her work was completely ignored? It was. And not just because she was a woman doing science in 1856, but also because she was an American when all science was done in Europe, and she wasn't at a university. Where'd she do the experiments? In her kitchen. So it wasn't until 3 years later when a man working at a university laboratory in Europe, John Tyndall, did the exact same experiments that it was like, okay, I guess it must be real. Showed that CO2 and water vapor, other things in the atmosphere absorb and then re-emit heat, what we call the greenhouse effect today. And there it sat for 30 years until this guy came along, Svante Arrhenius, giant in the world of chemistry, won the Nobel Prize in chemistry for his work in 1896, showing that human-caused CO2 emissions from burning fossil fuels could be large enough to cause global warming. This is like, that's how little this is actually being debated, really. We completely have understood this for well over a century. Now, modern science has built on this, but the physics and chemistry were well in hand even at the beginning of the 20th century. There it sat for 60 years until this person came along. Charles David Keeling, 1958, professor of atmospheric science at UC San Diego, the Scripps Institution of Oceanography. And Keeling was the first person to say, you know, we need to have a continuous record of CO2 in the atmosphere. We can't do good observational science without having a measurement at least once an hour. And so they started to record once an hour the concentration of CO2 in the atmosphere down in La Jolla, where UC San Diego is located. And they immediately realized you can't do this in a city. You need to be out somewhere far from people. Otherwise, you're measuring emissions from rush hour on the 5 in San Diego. So he put in for a grant to move his laboratory from La Jolla, California to Hawaii. Now, I can tell you, as somebody who's put in grant applications, I can only imagine what the reviewers thought of this. If you've been to La Jolla, it's heaven on earth. And so here it's like, oh, that's not good enough. You got to move to Hawaii. Is that the idea? The reason he wanted to move to Hawaii wasn't the beaches, it was this. The two giant shield volcanoes on the big island of Hawaii. That's Mauna Loa and Mauna Kea. They rise up halfway through the atmosphere, and his idea was to put a laboratory up on the top of these mountains. You're 15,000 feet up in the middle of the Pacific Ocean. You're not going to get data that's influenced by a city. And that's exactly what he did. Here's what the lab looks like. And so, starting in 1958, right through to the present, we've got a continuous record of CO2 in Earth's atmosphere. Remember, CO2 is responsible for about 2/3 of climate forcing. And this morning I downloaded the most recent data. Whoops, wrong button. Here it is. So this is that's today, March 19th. Here's the week ending, March 19th. So we are right there looking backwards over 1 week of time. There's a gap in the data, I don't know why. Vertical axis is concentration of CO2 in the Earth's atmosphere in parts per million. ppm may not sound like much, it's plenty. These are pretty potent gases. And if you look for a pattern, you probably won't see one. It's pretty level there for that 1 week. So let's look at a longer period of time. Here we are now, today, March 19th, looking back a month of data. So there's CO2 in the atmosphere a month ago. If you use your imagination, you might see some pattern in this. Maybe it's trending up or maybe it's trending down. It's hard to see. It's only 1 month of data. Let's go back farther. This is 6 months. Again, here we are today. This is 6 months ago, last fall that is. And at this point, you can clearly see a pattern, which is rising concentration of CO2 in Earth's atmosphere. Now, by the way, you could make this measurement anywhere on the planet. The research in Hawaii up at the top of a volcano, it's just the oldest continuous, or I should say longest continuous record, but you get the same results if you measure this anywhere else. And so this is really handy to have. Let's look at a longer period of time now. Here's 1 year. Uh-oh, it's complicated. So here we are a year looking back to a year ago, and what it looks like is that CO2 was rising and then falling and then rising again. And anybody know why it does that? Hint, it has nothing to do with people. This has been going on for hundreds of millions of years. Plants are growing. It's photosynthesis. So plants, green plants, when they photosynthesize, they're using energy from the sun, they're using energy from the sun to combine carbon that they take in the form of CO2 from the atmosphere to form all kinds of organic compounds, and using other ingredients that come up through the roots, like water and other nutrients. So during the growing season in the northern hemisphere, that would be from about May to about October, CO2 in the atmosphere goes down. And in the rest of the year, it goes up because leaves fall off trees and decay, grasses die and decay, other organic material dies and decays, and so all that CO2, biodegradation, just goes right back into the atmosphere. And so this cycle is the cycle of plants growing, CO2 goes down, and dying, CO2 goes up. That's 1 year cycle. Let's look at 2 years. So the zigzag is familiar. Winter, summer, winter, summer, winter. But there's something else going on now too. Can you see it? It's on a slope. You have to look for a second, but you'll see it. The highs are getting higher, and the lows are getting higher. That's us. We're adding CO2 to the atmosphere, so that sawtooth pattern is on a slope that's going up. Okay? That's us. That's our signature. Do you remember what year Keeling started recording this? 58. Yeah, so we have a continuous record from 1958. Would you like to see it? Everyone's going, no. Here it is. Some hoax, huh? Yeah, so this is what we call the Keeling curve. It's a record of CO2 concentration in Earth's atmosphere. The zigzag is the annual cycle of the seasons, plants growing and dying, growing and dying. That's the sawtooth. But the slope, that's us. And we know from other evidence that there isn't some other thing that's driving it. It's not like a sudden increase in volcanic eruptions. We would know about it. And geochemically, we know that it's not volcanic gases. It's fossil fuel that's being burned. And there's some other evidence that makes it unambiguous. I also want to put a line here as well. You remember earlier we looked at emissions were rising pretty much steadily, and I just stuck a red line there. Here, this is not a straight line curve at all. It's an exponential. And if you suffered through calculus in high school, you know why this has to be an exponential. Because in that earlier curve, in that earlier plot where we show emissions are always increasing, well, if you're always increasing faster and faster what you're adding to something, you should expect an exponential curve, and that's exactly why this growth in CO2 in the atmosphere is not linear. It is a power function. It is an exponential, okay? Well, it turns out we can go back farther than 1958. We can go all the way back to the year 1700, and we do that using the geologic record. We drill into the ice sheets in Antarctica and on Greenland, and as we drill down, we're going back in time. And the farther down you go into the ice pack, the farther back in time you go. And the ice, if we bring an ice core up to the surface, there are air bubbles trapped in the ice, which are left over from winters hundreds of years ago or more. And so based on the composition of the gas in those air bubbles, we can very easily, we're directly measuring what was the CO2 concentration in the atmosphere back in 1700, and it was down there. It's around 270 parts per million, not 430. Okay? So we humans have increased the CO2 concentration of the atmosphere about 50% since the pre-industrial era. The steam engine was invented in 1788, I think it was, somewhere around here, by a guy named James Watt in Scotland. Prior to that, we were not burning fossil fuels. And in fact, as you already know, we weren't really burning fossil fuels until the mid-20th century, until about 75 years ago. We can keep drilling back farther in the ice. Here we're going to the year 0. Pretty much constant CO2 until pretty recently, the industrial era, but really in the 1950s it started to take off. The Keeling curve now is nearly vertical. We can keep drilling farther back into the ice. We're now going back 10,000 years. This is the whole sweep of human civilization. 10,000 years ago, there were people. We were hunters and gatherers. We hadn't domesticated any animals for food at that point. We were just learning how to farm in a very primitive way. And metallurgy was still 5,000 years in the future. That's what it was, the human existence was like 10,000 years ago. And you can see that actually CO2 has been fairly level until really the 20th century, and then it shot up. Now is probably a good time to tell you that CO2 and temperature move in lockstep. If one goes up, the other goes up. If one goes down, the other goes down. There might be a lag of 50 years, maybe 100 years. There's a little bit of latency there for feedback reasons, but if one goes up, the other goes up. CO2 goes up, temperature must follow. And that's exactly what started to happen in the past few decades. CO2 started to rise seriously at about 1950 onward, and temperature has started to rise on our planet since about 1950 and onward. Even if we stopped emissions completely today, temperature would still rise for a while longer. But of course, we're not stopping emissions today of CO2 or any of the other greenhouse gases. So we should certainly expect temperatures to continue to rise. There's no way around it. CO2 and temperature move in lockstep. If one leads, the other follows. If one goes down, the other follows. Okay. We can go back more than 10,000 years. We can go back about 800,000 years by drilling all the way through the ice sheet in Antarctica, a place called Vostok, it's the Russian word that means east, until we hit rock. And at that point, that's as far back as we can go in the ice record. And what you see is the warming, cooling, warming, cooling, warming, cooling, warming, cooling, warming, cooling, warming of the Ice Age. The Ice Age was not a single period where the Earth was covered by ice. It was a period where about every 100,000 years we would go through a glacial expansion and a glacial retreat. Glacial expansion and retreat, and that's what shows up here. CO2 levels down around 180 parts per million, that's cold. CO2 up around 270 parts per million, that's warm. That's what your grandparents were born into, that kind of level, so-called interglacial period. Here's a little chart that maps CO2 concentration in blue and temperature in red superimposed on each other, and you can see Yeah, they don't map exactly, but they're pretty darn close. And Earth history going back 400,000 years, it's not like we don't have any evidence of what happens when you increase CO2 in the atmosphere. We've got really good evidence of that. And it shows up nicely in the ice record and in some other geologic evidence as well. Okay, now the takeaway here is that going back 800,000 years, meaning before there were Homo sapiens, this is not like before the Egyptian pyramids were built. This is before there were people. Earth has been in a range of cold and warm throughout the ice ages, right up through to about 1950 or so, and we have completely split that system. We're not in that system at all anymore. There's not going to be like an ice age that happens any day now and it'll save us. We've split the system. We're no longer in that kind of regime. You can also tell by going back to this slide that the temperature swings between cold and warm during an ice age was some on the order of maybe 6 to 8 degrees Celsius. Okay? And that's all it took for the planet to go from, very warm and pleasant to pretty darn cold, especially at higher latitudes. So we know that these swings here were on the order, let's call it 6 degrees Celsius swing. How much of a swing is that? Well, it turns out to be a log function, so it's not quite as simple, but it's probably on the order of 3 to 5 to maybe 7 degrees of warming, of which we've experienced about 1.5 degrees so far. Okay. So where's all the CO2 coming from? Well, the carbon's coming out of the ground. This is natural gas here. We're burning natural gas in the presence of oxygen, produces water and CO2. This is a familiar compound to you. This is octane, which is what I use as a stand-in for gasoline. Gasoline is a blend of all different kinds of compounds. The only one that everybody knows is octane because that's how gasoline is priced, but it'll do. All hydrocarbons, coal, oil, and natural gas look just like this. They're made up of carbon and hydrogen in varying ratios, which is what the numbers are. That's all it is. Hydrocarbons made of carbon and hydrogen. And in every case, when you burn them in the presence of oxygen, you get water and CO2. Water and CO2. This is why on a cold day, if you have a gasoline-powered car, on a cold day, you'll see water dripping out of the tailpipe. Like, where's that coming from? It's the water of combustion. You're burning gasoline, and the waste product is water and CO2. The CO2 you can't see, but the water is dripping out, and as your engine gets warmer, the dripping stops. It's now coming out as steam rather than liquid water. But that's what comes out of a tailpipe, is water and CO2. The same with a coal-fired power plant, natural gas-fired power plant, jet engine, anything that's burning fossil fuels, you get CO2 and water. So the carbon, you already know, is coming out of the ground in an oil field or a coal mine. Where's the oxygen coming from? Because we're combining these elements with oxygen. The answer is the atmosphere, which means we must be consuming oxygen in the atmosphere. And we are. Here's what it looks like. So this is the ratio of oxygen normalized to nitrogen, and it's declining. Why? Because we're combining oxygen, free oxygen, the stuff you breathe, with carbon to make CO2. And we're combining some of it with hydrogen to make water. The water we don't care about because it comes out in the hydrologic cycle. The CO2 pretty much stays in the atmosphere indefinitely. Okay? By the way, Julia mentioned that I give talks to companies. This is the slide where executives look up from their phone. They go, wait a second, can we go back to the beginning again? Are you telling me that we're using up oxygen? So we're not using up the oxygen in the atmosphere. We're reducing it, but everybody's got a favorite element, and I'll tell you, for most people, it's oxygen. All right. So part 3, and then we'll jump and take some questions. If we were to look at the other greenhouse gases together, fossil CO2, methane, nitrous oxide, those fluorinated gases, and this horrible acronym, Lululemon, It's land use change, and forestry. It means reforestation, deforestation, land use, alteration, all lumped together into this one function. If we were to put these together and normalize them so that they, as if they were all CO2, you get this kind of chart. And this is why we're saying this is greenhouse gas emissions, say the past 30 years or so, gigatons of CO2 E means equivalent per year, and you can see generally it's been rising. But the real story, and you can see it sort of with your eye, this dark gray color, fossil CO2, that's the bulk of the growth. Methane has gone up, nitrous oxide somewhat, the fluorinated gases, sure, but really it's about the burning of fossil fuels. How long have we known this? A long time. So I think we'll skip this and take a look at temperatures specifically before we go to Q&A. There are globally 5 gold standards for climate data, 2 in the US, 2 in Europe, and 1 in Asia, and there's new ones that are emerging. The 2 in the US are NASA and NOAA. The 2 in Europe are 1 in the UK, which is the British Meteorological Office, the Met Office, and 1 that the EU operates called Copernicus. The 1 in Asia is the JMA, Japanese Meteorological Agency. These are gold standard enterprises that have their own satellites, their own data collection and analysis. The Chinese have introduced one recently. There have been other ones that are introduced as well. I'm going to use the NASA data set here as one of the gold standards just to look at temperature. And in this case, I've plotted using NASA's annual average temperature, temperatures from 1880 to 1900. The blue dots simply indicate global temperatures that I'm going to use as my benchmark, my 20-year benchmark, and we're going to see what happened over the next century or so. So the first 40 years of the 20th century, from 1900 to 1940, actually there was a little bit of a cooling trend and a little bit of a warming trend, but nothing terribly significant. Plenty of cold years, plenty of warm years. The next 40 years was entirely different. From 1940 to 1980, there were no more cool years. There's no blue dots below the 0 line. Every year was warmer, and now the average is about the same as the warmest years that were recorded previously. This was the first sign that maybe we were seeing warming. Okay? Here's the next 20 years. Well, that's interesting. From 1980 to 2000, now it looks like there's an upward trend, not just a shift upward, but your eye wants to draw a line through this. In fact, it's hard to prevent your eye from not drawing a line through that. Here's the next 15 years. Now it's really hard for your eye to not draw a line through this that would indicate the year things are warming up. You'll also notice something else that's happening here. It's a little subtle, but temperature sometimes gaps up and then kind of stays there. And you'll see this again and again. When the temperature gaps up, it's often because of El Nino. So El Nino is a phenomenon in the equatorial Pacific that you've certainly become familiar with. We're probably moving into an El Nino towards the end of this year. It's an event where the ocean gives up a bunch of that heat that it's been storing, and it warms the whole planet as a result. It's a band of equatorial Pacific from the Solomon Islands all the way over to South America, and that event's called an El Nino event. And that's a big El Nino year right there, 1998, and then there's others, but we'll see that pattern again and again. Here's the next few years. There's that gap up again. Again, there was a big El Nino year, and then we stayed there. We didn't come back. It was like, okay, now it's a new regime. This is very different from the first half of the 20th century. In fact, it's even very different than what we were seeing here for these 40 or 60 years. So there's 2022. Let's put the most recent years on there. There's 2023. There's 2024. I'm resisting not having to redo my graphs. There's 2025. Okay, I'm saved by the day. But you get the picture. This is why the last 3 years aren't just the hottest years ever recorded. They're much hotter than we've recorded previously. And although it's in fractions of a degree Celsius, they're very different, okay? So these are some of the slides that we could post these or somewhere, right? Distribute somehow? Okay, so you'll find in this sort of bonus section at the end other charts that show the same kind of thing that we've been discussing. And we're going to skip this business about other greenhouse gases because I've already commented on it. And here we go. So part 5, this is what I'm going to point you towards. These are the green shoots that I mentioned earlier. It's been apparent for the past few years that because renewable energy has gotten so cheap that there's a transformation, a green transition that's happening. And this was published just a few weeks ago in the New York Times by this person who, in my view, is absolutely outstanding climate journalist. And of course, here's the link. So if you haven't read it, please do. It's a nice cataloging of the green shoots I've been referring to. Now, it doesn't quite fit the narrative that we as Americans would like to hear. So the narrative that we'd like to hear is something like 2 really cool guys in Palo Alto discovered an element between carbon and nitrogen, element 6.5, and nobody knew it was there. And it turns out it gives infinite power. We're done. Nothing has to be. We're done. That was it. We solved it. That's not what's happening. Or that, you know, something about government policy changed, perhaps. But I want to just rattle off a few of these green shoots, and then we'll leave it there. So there is this. There's a lot to be depressed about. You know, we just a couple weeks ago revoked the climate endangerment finding, which basically says everything Drew just talked about, all of the geologic evidence, all of these empirical facts, we're just going to pretend they don't exist. We're going to solve this problem by pretending there is no problem. I don't think that's going to stick, but there you go. These days, people talk about energy affordability. If you're still buying gasoline, you probably are talking about it too. It's gotten crazy expensive, not just here, but especially in Europe and in Asia. Europe is importing record natural gas. That includes from the US and elsewhere. China's building more coal plants than anywhere than they ever have. And world leaders are skipping climate conferences. I would too. You know, there's not much that happens there. So these are all things that are sort of concerning. But here's what's also happening. Over 90% of the new power capacity that's being built worldwide is solar panels and wind turbines. That's really happening, in spite of all of the bad news that's on the left-hand part of the slide. In fact, there's about a 10-to-1 ratio of investing in clean energy relative to fossil. That's really happening. You wouldn't think it, but that's actually occurring. In fact, even here in the US of A, about 90% of the new capacity that's being built this year in the US, in spite of all of the bans and this and that, is solar and wind. You'd think, oh, it's gone to zero. No, it's actually the majority of new power generation that's being built. Electric vehicle sales are up 30x since the first really commercially viable electric vehicles were introduced a decade ago. And the International Energy Agency sees that about 90% of new electricity capacity over the next few years will be solar and wind. Why? Because it's cheap. When I started teaching about this class 20 years ago, solar panels were what were they? $10 a watt. That means if you wanted a solar panel that generated 200 watts, which would be state of the art at that time, it was $2,000, $10 a watt. Today, solar panels, about 30 cents a watt. That's a 97% price drop. This is there's a word for this. It's called capitalism, and it's driving down prices so dramatically that's what's driving the widespread adoption of green energy. How big is this? Well, the story's mostly China. Again, it's not a narrative that is the narrative we'd like, but it is what's actually happening. Last year, 2025, China installed more solar panels than exist in the United States. In fact, China in 2025 generated enough electricity from solar panels to power the United States for the whole year. So it's not that it can't be done, it has been done, just not here, but it has been done. And the reason, it's cheap and it gives you energy independence. I'll close by quoting one of my professors, Henry Pollack. He said, you know, the Stone Age didn't end because we ran out of stones. The Stone Age ended because we found a better way to get things done without using stones. And that moment, in my view, is the moment that we're in right now. I can keep going with statistics. You'll see some more in the slide deck. It's Q&A time.
It's Q&A time, and we only have about 10 minutes. We're committed to getting you out in time, but don't worry, because not only will we send this out, but we will also send you the dates for when you can come and talk to Drew Moore. So your first question, great segue. I have solar panels, Tesla Powerwall, 2 EVs. Do these three things actually help Earth or not really?
Oh, sure.
That's it.
Is that my wife who wrote that? I mean, where are you? You wrote that's us.
No, it wasn't.
Yeah, of course they do. You know, you could go green for electricity by signing up with MCE Deep Green, or PG&E has something similar now too. So you don't have to put solar panels on your roof or backyard to get off the grid. The other reason you want to do it is it'll save you money in the long term. Price increases from PG&E don't matter to you because you're generating power, you're storing it in batteries. Oh, and by the way, PSPSs, I think they're called, power shutoffs, won't affect you. You know, we were without, after the 2020 fires, we had no grid for 4 months. Didn't matter. So there's a resiliency aspect to it, as well as saving money, but there's no question that is, you know, less demand on PG&E, good.
I'm going to try to paraphrase some of these so we can get through more. So there are many natural climate processes that drive climate change, even pre-existing humans. How do we separate those from the human impact?
It's actually remarkably easy. The main way is the time constant. So the main thing that controls the Earth's climate over the long term is plate tectonics. With the motion of the plates, which move at about 1 centimeter per year, it's a good number to sort of average. The Hayward Fault, San Andreas is about 1 centimeter a year, maybe a little more, but that isn't even glacial pace. That's slower than a glacier moves. So the time constant gives you that answer. There is no natural phenomenon like volcanoes or other things that operate at the kind of rate that you saw with the Keeling curve. There is no other explanation. There is a more scientific proof that was worked out in the 1950s, again at UC San Diego, that demonstrated this is going to get a little geeky here, the isotopic makeup of carbon in the atmosphere clearly indicates the burning of fossil fuels. And it's famous research that was done in the 1950s. It was actually one of Keeling's older colleagues at UC San Diego. And since then, we've replicated this over and over again. So there's no natural phenomenon, not volcanism, nothing else that operates at the pace of change that we're observing.
Is it true that one way of reducing emissions is if everyone ate 1 less hamburger a week?
1 less hamburger a week? How much you eating? You know, I love these personal questions are really awkward. It's like, tell me that my grandchildren will live a happy life, you know, not with you as our grandparents, they won't. Yeah, I mean, so I skipped the slide, but it's in the deck that you'll get. The human diet is responsible for about 30% of climate change. And of that, 3 things account for most of it: beef, dairy, and rice. Why beef? Because cows are ruminants. They ferment grass, they burp out methane as part of that fermentation process. Methane is a potent greenhouse gas. They're ruminants. That's true for sheep and goats as well, but cows are the big ones. Dairy, well, see beef. It's the same animal. Mostly it's milk cows. Rice, because rice is the only grain that you have to flood the field. And when you flood a field, all the organic material in the soil goes from aerobic to anaerobic decay. Microbes do that, and the anaerobic decay results in methane releases. So, what are the big 3? Beef, dairy, and rice, or methane, methane, and methane. Everything else is almost climate neutral, very close to being climate neutral. Fish, pork, chicken, obviously fruits and vegetables, nuts, all that stuff. It's so the whole part of your diet that you might want to look at would be beef, dairy, and rice. Americans don't eat rice, not like the rest of the world does.
What will AI do to the carbon curve despite the China fuel reduction?
What was that?
What will AI do?
So my initials are AI, so I'm assuming.
Artificial intelligence.
I'm still waiting for a job at OpenAI. Yeah, so AI, as you doubtless are aware, is very compute intensive. And it is therefore very energy intensive. So the AI build out that's happening really in 2 places, the United States and China, is an issue in the United States because we're not building energy as fast as China is. Right now, China is building not just a lot of coal plants, I mentioned that. China has 35 nuclear power plants under construction right now. The US has none. And that is relatively low carbon, very low carbon source of electricity. So China, it's not really going to be an issue. Our AM models are better this year, but we don't have much electricity. China's models seem to be a little behind ours, but they have plenty of electricity resources. The build out over time for powering AI is going to be renewable because it's cheaper.
We've got one last one, or time for one more.
Sure.
15 plus years ago, companies were enthusiastic about carbon credits. Where are we now with carbon credits?
They've been shown to be nonsense. I mean, there are carbon credits or offsets that in the voluntary market that are meaningful, but a lot of them are just really don't do anything. And so it was something that companies were proud of until it started to be shown that actually they're ineffectual. And so there are offsets that do have impact, but the overwhelming majority of them do very little. Okay.
Thank you again to Drew. This is not your last chance to see him. We'll be sending out information. We have dates.
Thank you.
And from our good friends, Donine and Bill Dyer, got a little treat for you for coming out tonight.
Oh, thank you.